This is video help for problem 27.4. We don't actually have homework advice for this with numbers or anything, so I'll try to give you some idea. But these are straightforward calculations, and I'll just give you order of magnitude. In part A, then, we're talking about a old-fashioned resistive magnet with currents, with resistors, not superconducting, and it's good old electrical circuitry with resistors and DC currents. You know how to calculate power. You're going to get millions of watts, megawatts. And in part B, then, when you do your how much water will you heat up to 75 degrees Celsius, you're going to get hundreds of liters, and that actually means you need to do serious cooling here. You can't just let this thing heat up. In fact, gradient coils with far less current in them need to be cooled, and this would be just prohibitive. So we do go to superconducting, magnets. In part C, we look at just how big this thing would be, and you're going to get thousands of kilograms of copper. So you've got tons and tons of copper. And remember, you've got to have that whole heating system, and you've got all kinds of other things to be added into this. For a superconductor, by the way, there was a typo. It should be 2.5 grams per centimeter cubed. The current is 15 times in these numbers. Our numbers here are not necessarily representative of present day numbers, but this still gives you a sense of the difference here. With the current 15 times, then you're going to get an order of magnitude less in weight. Still, in today's superconducting MRIs, you've got tens and kilometers and more of wire. The comparison, though, is really evident now. That you've got the current goes up for superconducting, your weight goes down, your power is really down. That's it right there. Oh my gosh, you do not have to keep pumping in power for superconducting magnets, and that in itself is a huge thing. And stability of the field. That's another thing that we're not mentioning here specifically, but to get a magnet to sit there for hours and days and keep a nice uniform constant field, that is unparalleled advantage for superconducting magnets. In part D, if you just go back to freshman physics, the B0 in the center of a loop, how does it vary with the radius? And actually that's the same behavior that you're going to get in the constant term in equation 27.5, which is a field due to loops and off center, but it doesn't matter. And in the center of the concentric loops. And also note how it depends upon if you had n turns. How does that B field compare with? How does it depend on ni? So if you double A, if you have A go twice the value, what does B0 do? And therefore, if you need to maintain the B0, what do you have to do to n? And therefore, what does it do to the weight?